Hi guys! First of all, thank you very much for joining the course. I packed it with as much knowledge and content as possible. Hopefully you'll get a lot from it. If you want to go deeper in the subject later, why not even work into that area? I hope this course will help you achieve your goals. In this lecture, we'll look at the fundamental physical laws and principles behind rockets. So basically, what are rockets? What defines them? We'll look at the Newton's laws of motion, which I'm sure a lot of you will already have heard about. We'll also look at the rocket equation, which is probably the single most important equation in the whole of rocket theory. First of all, let's talk about combustion, or what is commonly known as burning. Well, combustion consists in two chemicals, a fuel, which is usually an organic compound like petrol or methane, which you burn in your house to produce heat, and an oxidizer, which is usually oxygen taken from the atmosphere. This fuel and this oxidant react chemically and produce two things. First of all, heat, and that's why this kind of reaction is called exothermic. They produce a lot of heat, and an oxidized product, which is basically the result of this fuel and oxidizer reacting together. And for example, in cars, this is carbon dioxide, carbon monoxide, among other things. What is really interesting about rockets is that rockets are any matter which contains its own mass to expel and its own oxidant. So to give you a comparison, if you look at airplane's engine to function really need the fuel, obviously, but they also really need the air in the atmosphere. And that's because they need that air to burn the fuel, and they also need that air to have mass to expel out their back and move forward. A rocket does not need that. A rocket does not need anything external to itself to function, and that's why it can work in the vacuum of space, which is completely, almost completely empty. So let's see how combustion, or burning, comes into play with rockets. Basically, in a rocket, the propellant is the fuel and the oxidizer. And as they react together through combustion, they create the oxidized product, which is expelled out the back very fast thanks to the heat created by the reaction of the fuel and the oxidizer. So combustion, like in a car engine and an airplane engine, is a central process within rockets. Now let's look at the Newton's laws of motion. I'm sure most of you will have heard about Isaac Newton. He's one of the father of classical physics and classical mechanics, a very important guy in modern physics. So the first law states that an object either remains at rest or continues to move at a constant velocity unless external forces act on it. That basically means that if you have an object that is moving at a certain velocity and no other forces are acting on it, so when you're on Earth there's drag and all kinds of friction, but if you're in space, something that's moving, if no forces at all act on it, will always keep moving. It won't accelerate, it won't decelerate, it will stay at the same velocity. If you look at the second law, it states that the sum of external forces applied on an object is equal to the mass of that object multiplied by its acceleration. F equals ma. So that means that if you have a mass of an object, so if you have an object whose mass you know, and you know its acceleration, you can know what force is applied on it. On the other hand, if you know that same object's mass and you look at the force that is applied on it, you can calculate an acceleration. This also means that an object will only accelerate, so an object of a certain mass will only accelerate when an external force is applied to it. The third law states that if a body A exerts a force on a body B, then that body B exerts an equal force in magnitude and opposite in direction on body A. It's really easy to feel that in real life actually, because if you go against a wall and start pushing on the wall, then hopefully that wall will not move. And that allows you to really feel how the wall pushes back on you in the exact opposite direction that you're pushing on it. And that's a very important concept in physics, because that's what we use in almost all transportation technologies. So cars, as their wheels turn, the wheels push on the ground and the ground pushes back the car, which moves forward. So let's look a little bit deeper into the second law of Newton. As we saw, it states that the external force is equals to the mass of an object it's applied on times the acceleration of that object. We also know that acceleration is the time derivative of velocity. So I'll assume most of you know what a derivative is, but in case you forgot and as a little explanation, in that case, it means that acceleration is basically the rate at which velocity changes with time. So if you have an increasing velocity with time, you get a positive acceleration. If you have a decreasing velocity with time, you get a negative acceleration, So we can rewrite our equation as F equals mass times the times derivative of velocity. And by doing a bit of math, you get the external force is equals to the time derivative of the product m, so mass times velocity. So that product is actually very important in physics. It's called linear momentum, and it's usually abbreviated by the letter P. So what is momentum? Momentum is basically the resistance of an object to a change in its state of motion. What does that mean? That means that basically if you have an object of a certain mass m moving in a certain velocity and in a certain direction, if you try to change that object's velocity or direction, then you will feel a resistance. And that resistance is called momentum. It is proportional to the object's mass and its velocity. So the greater the velocity and the greater the mass, the bigger the momentum and the bigger the resistance. It's also very interesting to note that writing the second law of Newton like this gives a new definition for what a force is. Basically, it states that a force is the change of momentum with time. It is the time derivative of linear momentum. So let's look at how the laws of Newton apply to rockets. The equation we just saw that states that force is equal to the time derivative of linear momentum essentially means that the force exerted on an object depends on how fast the mass and or velocity of this object is changed. That's essentially the second law of Newton. So if you take a rocket, which is ejecting a small amount of mass at very, very high velocities in a direction that we will call B, then according to the second law of Newton, this ejection of mass is actually creating a force. And according to the third law of Newton, this force is applied to the rocket in the exact opposite direction of B that we will call C. Finally, according to the first law of Newton, the rocket will keep accelerating in the direction C as long as that force keeps applying to the rocket. As I mentioned briefly previously, the rocket equation is probably the most important equation in the whole of rocket theory. It's also named the Tsiolkovsky's equation after the person that first derived it. It essentially tells us the change of velocity that a rocket can achieve, which is the single most important thing in the whole of orbital mechanics. How much velocity is our rocket going to achieve? So the equation is written that the change of velocity delta v is equal to the exhaust velocity c times the Neperian logarithm of the initial mass of the rocket over the initial mass of the rocket minus the mass of fuel ejected, written delta m. So the only things that affect the rocket velocity or its exhaust velocity, or how fast it throws material out its back, and its ratio of initial mass to final mass, or basically how much fuel it's burned and ejected at the back. And this is why mass is so important in rocket design. This graphic offers a plot of the rocket equation for different rocket exhaust velocities, which, as we just said, is basically the speed at which material is coming out at the back out of the engine of the rocket. So as you can see, the gray line represents a 2000 meters per second exhaust velocity, the red light a 3000 meters per second exhaust velocity, and so on. The vertical axis on the left represents the change in velocity achievable by the rocket. So basically from 0 to its maximum achievable velocity. The horizontal axis represents the mass ratio of the rocket, which is basically its initial mass divided by its final mass after all the fuel has been burned. The horizontal dotted line, which is fixed at approximately 8000 meters per second, represents the minimum velocity needed to achieve a low Earth orbit. And what this graph shows is that actually, to achieve such an orbit, a mass ratio comprised between 5 and 8 is needed at the exhaust velocity quoted below, which are typical chemical exhaust velocities. This basically means that in order to reach low Earth orbit, with available current technologies, a rocket's final mass has to be 5 to 8 times smaller than its initial mass. This means that a lot of fuel must be burned in order to reach low Earth orbit, and it also means that a comparatively low weight of payload can be carried to space. This is very important, guys, because these are basically the two biggest challenges in rocket design. How do we get a faster exhaust velocity, or how do we get a greater mass ratio so that we can carry more payload to space for less fuel? I hope all of this was clear. If you have any questions, do not hesitate to ask me on the platform. You can also email me and I'll be very happy to help you. The next short lecture will actually go through the derivation of the rocket equation for those of you that are interested. Otherwise, you can skip straight to the third lecture, which will talk about specific impulse and efficiencies, which are also very important for the next lectures to come about rocket design.